Last problem on the set, problem 8, the trapeze artist problem. So it says, hey, a trapeze artist of mass m, holding the bar of a trapeze suspended by 2 ropes of length L, steps off a platform with initial angle to the vertical of theta I. That's our initial angle mixed with the vertical. We want to show that when the ropes make an angle theta with the vertical, the artist must exert a force equal to this expression to hang on. And then part B, we want to find the angle for which the force required to hang on at the bottom is twice the artist's weight. So here we go. Let's go with part A. The first thing I'm going to do is draw my sketch. So I'm going to get myself some blank paper and draw my sketch. All right. So let's see here. So it's like a trapeze, right? And the guy hanging from the trapeze. But you know what this guy on the trapeze swinging is like? It's just like a pendulum, right? So it's going to look quite a bit like the diagram for problem 7. Okay, quite a bit like it. Again, I'm going to draw it nice and big because I'm going to do a lot of geometry on this sketch. All right. So here we go. Okay, pretend that was a straight line. All right. Hey, look, there's the trapeze artist. Okay. And it's going to swing down. All right. All right. Pretend that was a nice curve. I'm sorry. So the length here is L. And this whole length here is L, right? It just swings down, right? Okay. Now, this starting angle here, all right, we're going to call that angle theta I. Okay, that's our initial angle. Now, we're also looking at a little bit later. It's going to have swung down to some new angle here. All right, this one we're just going to call theta. So we're going from theta I to theta, from here to here in this calculation. Okay, swinging along. I did not do a good job drawing that, but you get the idea. Okay, and we want to show when this thing gets to that angle theta, that's the force that you have to pull, that's pulling on your arms. So we're starting here and going ending here, right? Okay, marking our starting or ending positions. Okay. So if we're going to do an energy calculation, we know we care about what forces are acting, so we can see whether they're doing work and pumping energy in or out of the system. So I need to do a force diagram for it while it's in the process of swinging along here, okay? So this is my trapeze artist, okay? And technically there'd be this force on his hands, right? Tugging upward, right? Kind of at this angle, right? Now at some generic, I'm going to draw this actually for at theta, okay? Then we know the angle the rope makes with a vertical is theta, all right? Which means technically the angle it makes with the vertical here would be theta, right? Okay, I'm going to call this just tension, okay, on his arms. Is that okay? Then it's going to be his weight going down, mg. Okay, and those are my forces. So I'm going to do something kind of tricky here. You know what? I'll do the energy thing first. Okay, so those are my forces acting, are T and mg. Let's go. Yep. Let's go to our work energy theorem. So we're going to say, hey, if I add up all my work terms, that's equal to the change in the kinetic energy. And we're going from here to here, right? And so you say, well, there's going to be work done by that tension and work done by the gravitational force, and final kinetic minus initial kinetic, expanding out that delta. And you say, wait, some of these terms are going to be 0. You say, hey, that tension, it's always acting perpendicular to the velocity, right? It's perpendicular to the motion as we go along here, tangent to our path. That's radial. Radial forces never do work. So this work by tension going to be 0. We're starting from rest. At this point, V naught is 0, and then we let go, we're released and we start to swing down. So this, because V naught is 0, this term's going to drop out. This was because T was perpendicular to the motion. Okay, so now I'm just down to these two terms. Okay, this feeling good. It's starting to simplify out. I like that. I'm going to choose, because we're going on this weird curved path, trying to calculate the work done by gravity would be kind of a pain. We can do it. We know we would end up doing. We'd have to do like a change to be in terms of angle or something, change the variable of integration and blah, blah, blah with that integral form. Let's just avoid it. Let's just include the Earth in our system. So our system is going to be the trapeze artist and the Earth. So now this is no longer an outside force. It's a force between parts of our system. As we rearrange it, we change the potential energy. So of a UG final minus UG initial. Okay. So where am I going to call height 0 now? Because that might make one of these terms drop, right? Well, again, I'm going to have to figure out what these heights are here. And it's on this weird curving chunk of a circle. And I'm going to do the same trick that we did on problem 7. Okay. And if you haven't looked at problem 7 yet, go back and look at that because it's a lot simpler to see than the diagram I'm about to draw. So what we did was we drew across here, horizontal line, made a right triangle. This is a right triangle with theta I being this angle. So this vertical part here, this whole thing here is L. This chunk is adjacent to theta I. L is the hypotenuse. So this is L cosine theta I. So what's this length here? The whole thing is L. So this is L minus L cosine theta I. So what I'm going to choose to call this bottom spot here height 0. All right. So I'm going to call right here. Tick, 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 tick. I'm going to call here height 0. So my height here, the height I start at, is 0 plus this. So the height here I'm going to start at is L minus L cosine theta I. That is the starting height. I'm going to swing down to here. What's this height? So I'm going to draw across the line, horizontal line. Tick, 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 tick. All of this from here down to there. This then is the whole length L minus this chunk. What's this chunk? Well, hang on. This chunk, this is a right triangle here, this pale blue triangle, right? Right triangle, where this side is adjacent to theta, and this here, of course, is L. So this is L cosine theta. And so then what's this chunk here? Well, the whole thing is L, so L minus L cosine theta is this bit. All right, that's L minus L cosine theta. So that's my ending height is L minus L cosine theta. Starting height was L minus L cosine theta I. All right, so we can put those, so we are going to have both these two terms. Neither of these is going to be 0 because we're not ending here. We're going from here to here. We're trying to find the speed there. All right, so here we go. I'm now going to go ahead and expand out my terms. Oh, no, what the heck, I'll write it once. Sorry. Here is the work energy theorem showing only the non-zero terms. Okay, and that is something that I like you to always write. Okay, AP will look for this on the AP sheet. Okay, seeing just which terms are sticking around. Okay, let's put in our equations for each term. 1/2 mv final squared. That final velocity, that's, well, hang on, we'll come back to that. mg final height minus mg initial height. That's our formulas. I can put in expressions now for height final and height initial. That's what we just figured out here. That was what this trick was about. mg. You know what? It's okay if I factor out mg and I do height final minus height initial? Thanks. What's my final height? L minus L cosine theta. Minus my initial height, which is L minus L cosine theta I. Okay, that's my equation there. All right, and I hope you're thinking, gosh, we can simplify that a bunch. Okay, sure, you want me to do that right now? Sure, why not? Okay, so you see how I'm going to have L here and then minus this chunk so I can distribute that negative. So L minus L, those are going to cancel out. So then I'm going to have a minus L cosine theta, and then minus a minus makes it plus L cosine theta I. So that will turn into factor out the L. Okay, cosine of theta I minus cosine theta. Okay, and that L I factored out. Okay, now I've got, okay, sure. I'm going to move this to the other side, right? Which means basically I'm going to flip the order on these. So I'm flipping the signs. Does that make sense? No, just flip the order. So what I'm going to end up with is, you know what? Let me move the 2 over, multiply through both terms by 2 so I can get rid of that. Hang on just a second. While I look at the term I'm supposed to come up with. It's okay. I should have left it in there. It's all right. Okay, you could pause and verify that the algebra is good. Okay, but this is what I'm getting here. All right. And so you're like, hey, why don't you cancel that M out? Well, I'm going to save it there for my own secret reason, okay, that you'll see in just a second. All right. Tidy that up. There we go. No one would ever know. Okay, so here we go. So my goal is I'm trying to show, yeah, I should have done that calculation first. I'm trying to find the size of this tension when you get here to theta. Okay, that's what we're trying to find, is that stress on your arms when you get to theta. All right, so I'm trying to solve for this force. This force is a force along, now we're going in a part of a circle, aren't we? So we're going to be thinking radial and tangential. So if I'm thinking about that, I'm not going to split the tension force up. I'm going to split the gravitational force up into radial and tangential. There's right angles between the components. This theta would be this theta. So this is going to be mg cosine theta and mg sine theta. So when I do the sum of my forces in the radial axis, right? These two forces, T inward and mg cosine theta outward, they are not balancing out because I need to have an acceleration inward to make me turn, right? It's going to be mass times centrifugal acceleration, right? That's our formula for the radial axis, adding up the forces in the radial. And so I'm going to say, hey, forces in minus out is the way we do this. T, the thing I'm trying to find, minus mg cosine theta is m, and AC is v squared over r. All right. So that tension I'm trying to solve is going to be mg cosine theta plus mv squared. Now, that r, we recognize in this problem that r, radius of the circle, is just L, right? So I can just write that as mv squared over L. Now look, see, t is what I'm trying to find. See that mv squared? mv squared. Look at that. Look at that. So this term here, this thing is going to stick in where it said mv squared there. Do you see that? Look at that. I know I could have factored out the m and just substituted in for the v squared there. But anyway, so this is going to go and plug into this. Okay. So here's what that looks like. Tension is mg cosine theta plus, now it says mv squared. And I still have it divided by L. And then that business is coming up there. 2 mg L. Fine. Cosine theta minus cosine theta I. All right. That was really sloppy. Sorry. I hope you know what that says. Cosine theta minus cosine theta I. Okay. Hey, this L on top and that L on bottom, bam, bam, they're gone. All right, that's sweet. Now look, distribute this 2 mg. I got 2 mg cosine theta. Here's another mg cosine theta. So that tension is going to be a 3 mg cosine theta. And then I've got a 2 mg times cosine theta I. So minus 2 mg cosine theta I. All right. I got an mg in both terms. I'm going to factor that out. So my tension will be mg times 3 cosine theta minus 2 cosine theta I. And that is what we were supposed to show. Ta-da! Okay, I should have shown you the force calculation first, right? Because we're trying to find a force, and we got to this point, we had that v that we didn't know. We would have said, okay, let's find the velocity from a kinetic energy term and done the energy thing. I'm sorry, I did it backwards. I did the energy thing first and then that, sorry. But that's the logic that would have taken you through this problem. There was this tricky business of constructing these right triangles so we could figure out heights, okay? Which is a good skill to know. And then, of course, we used our radial centripetal acceleration formula, right? And looked at our forces in the radial axis here to get that expression for the velocity, because the velocity shows in the centripetal acceleration term. That's how we got the velocity, and that velocity we found with energy. So yeah, that's that problem. Very, very good problem. Okay, that was just part A, though. Okay, that was part A. Don't worry, part B will be quick-ish, I think. All right. Part B, what they want us to do now is they say, find the theta I for which the force required to hang on at the bottom is twice the artist's weight. So now we're starting from some unknown angle, theta I, and now we're going to talk about going all the way to the bottom. Okay, so now we're going to go from here to here. Okay, and we want to know what angle to start at so that at the bottom that force is double the weight, so that tension will be twice mg. All right, so I'm going to go ahead and draw a little bit more. Okay, do you want me to draw a new diagram or still work off the old one? Like, this old one's totally marked up. I feel like I ought to start over. So I'm going to draw another sketch real quick. All right, for 8b here. All right, so for 8b, and we're swinging. Okay. All right. This is an arc. Okay. This is not a diagonal line. Okay. There we go. All right. This is theta I. And we want to talk about when it's at the bottom of the swing. Okay. So we're going to when this is nice and vertical. Okay. Again, yes, I am going to end up doing this. and calling this, this is L, so this is L cosine theta I, and then this height here, this would be L minus L cosine theta I. Yep. Okay, and we're going to call at the bottom here, yes, this is where we're going to say, here the height is 0, and here then the height is L minus L cosine theta I. Okay, yes. Okay, now we're trying to solve for the situation when we're at the bottom of the swing here. So our force diagram, you say there's going to be two forces. There's going to be a gravitational force, and there's going to be that tension. We want that tension to be 2 mg, okay? We say we want that force to hang on to be double the weight, twice the weight, okay? So that's the setup. So I could do my sigma F equals ma, and this is while we're swinging in a circle. So we're looking at the radial axis here. So that'll be centripetal. We'll have forces in minus forces out. So it'll be 2 mg minus mg equals mv squared over r. Yeah. And so I see I'm going to get mg is mv squared. And the radius of this is L, right? That's the radius. You say, oh, look at that. This is going to simplify down real quick. You say, bam, bam, right? I can get that velocity at the bottom is going to be the root of GL. Okay? All right? Well, that's how fast it's going at the bottom. All right? But what I'm trying to find is what this theta I should be, that starting angle. Okay? Okay. This was at bottom of swing. All right, that was at the bottom of the swing. Okay, so we're trying to find that theta I. We're going to get that from an energy calculation. We are, of course, calculating going from here to here to the bottom of the swing, right? Okay, we're going to do our work kinetic energy theorem. So we're going to say sigma W is delta K. Work by gravity, work by tension is K final minus K initial. We know that that tension does no work because the tension is perpendicular to the motion at all times, because T is perpendicular to delta X. We know that our initial kinetic energy is 0 because V naught was 0. Right? We're starting from rest and swinging down. Okay. Okay, that trapeze artist. I'm going to make the system be the artist and the earth. So now this isn't an outside force doing work, but we are rearranging the parts of our system. So we're changing our gravitational potential energy, UG final minus UG initial. We're going to call down here height 0. So our final gravitational potential energy term is going to drop out because our final height is 0. That's nice. All right. So what do we end up with? There's only two terms: kinetic energy final and gravitational potential energy final. So I'm getting 0 is my final kinetic plus my final gravitational. How can these things add up to be 0? One's going to be positive, one's going to be negative. Kinetic energy is always positive. This is going to be negative. Oh, I just screwed that up. The final height is 0. Sorry. Final height is 0. Sorry. This is sticking around. This is a minus. Oh my gosh, that was really, really, really bad, Dave. This is UG initial that's sticking around. Sorry about that. Let's get rid of that stuff that we don't want. Sorry about that. Sorry. UG initial sticks around. Okay. All right. There we go. Sorry about that. Sorry, because we're starting here. We're ending at height 0. Okay. Whew. There we go. That makes sense. So yeah, this UG is going to be our initial. What did I just do? Minus that. Sorry. Yeah, that's a minus, right? Sure. Nah, yeah. No one will ever know. Okay, fine. There we go. Okay, so we can figure this out. 1/2 m v final squared minus mg times my initial height. Okay, and you say, okay, now wait. The whole thing here is I'm trying to figure out the angle I have to start at. Well, this is where we're going to get that angle in, is when we put in that expression for initial height. That L minus L cosine theta I. See, that's how we're going to get that in there. Yeah. So, and that's where we stick in L minus L cosine theta I. Okay. Hey, look, theta I is the thing I'm trying to find, isn't it? Now, did they tell me the length of this? Well, it's just, we're not looking for a numeric value here, right? Yeah, we're just trying to find, well, we'll see what happens. Okay, so let's see here. This V we don't know, but we have an expression for it here. So that's going to substitute in over there. Okay, so we'll go ahead and put this in there, right? So 1/2 m. Now v final squared, I'm going to take this root GL and I'm going to square it. I'm just going to take the root off, right? Take the radical off. It's just going to be GL. Okay. Minus mg. You know, I'm going to factor that L out. 1 minus cosine theta I. Look at this. What's in every term? There's an MGL in every term. So if I divide through by MGL, bam, 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 right? Look at that. Look at that. Look at that. There is a half minus, I'm going to distribute that minus 1 plus cosine theta I. What's a half minus 1? Minus a half. Move it to the other side. I'm going to have half is cosine theta I. You're like, oh my gosh. What angle has its cosine equal to a half? So I'm going to do an inverse cosine of a half to get theta I. And so I punch my calculator. I know, you already know what that is at the top of your head. I know. And yes, 60 degrees, of course, is the answer. Ta-da! We actually got a numerical value out, and they didn't give us any numbers. How's that? Pretty cool, huh? So this problem, we ended up using, look at all the stuff we used. We used sigma f is ma, but specifically did radial axis and like the centripetal acceleration formula, right? To find an expression for our velocity, because it's in that v squared over r part, okay? And then we did an energy calculation, right? And got that angle, right? Neat. Okay, we had to do a little bit of geometry here to find that height. Okay, a lot going on in this problem. Okay, that's problem 8. That's the last one on that homework set.